Welcome to a lesson with Dr. Powell. Let's take a look at how we can use matrices to help us rotate things in the plane. It has to do with this idea of linear transformation. And a matrix is a function that takes us from one thing to something else. In fact, if we think of the vector space R2 as the domain and the codomain being R2, we're looking at a bijective function that's going to just represent rotation. So if I'm here, the function that just rotates by a certain angle is actually a linear transformation, which means that it can be represented as a matrix. So I input a point in the plane, and the function or the matrix outputs something that's again in the plane, and it's the rotated image of that point. Okay, so let's think about this for a minute. Remember how we write down what a matrix represents. The first column is the image of the first standard basis vector. The second column is the image of the second standard basis vector. So meaning where does 1, 0 travel versus where does 0, 1 travel? We can think on a graph, 1, 0 is simply this position right here, 1, 0. Where does it travel? Let's suppose that we want to do just a rotation by 45 degrees or by force. So that would take us, we're on the unit circle, so that would take us right there, and the coordinates of this point are simply root 2 over 2 and root 2 over 2. Okay, so 1, 0 will take us there. All right, so that means that the image of E1 is simply root 2 over 2, root 2 over 2. And we're almost done with our matrix. We just need to know the image of E2. So we go to up to 0, 1, and where is it going to travel into the same rotation? Just over here, which is the same thing, but the x-coordinate is negative root 2 over 2, and the y-coordinate is the same, root 2 over 2. It's the same matrix, or it's the same as this, but you have a negative that is in this coordinate because that represents the negative x-coordinate here. Okay, so this is the matrix which represents the function of rotation by 45 degrees in the plane. And if you want, we can even rewrite this as square root of 2 over 2 times 1, negative 1, 1, 1. That would be okay as well. Thinking of this matrix itself as a vector, and this is being like a scalar. Now remember that matrices are functions, and functions in and of themselves that have an output as a vector space can themselves be thought of as a vector space under addition and scalar multiplication. This is a scalar multiplication just being factored out of it, and that's perfectly fine because matrices themselves can be thought of as vectors. All right, so let's see this in action. All right, where does the point, so let's just pick any point in the plane. You can pick a point down here. I mean, maybe we can pick a point like negative, let's see, negative 2, negative 1, all right? So negative 2, so negative 2, negative 1, something like that. Okay, negative 2, comma negative 1 in the plane. Let's see, where is it going to travel? Well, this is the function that takes us to where we're going to go, all right? So we simply take this and we input this into it. So what does this mean? This simply means take negative 2 times that column plus negative 1 times that column. Or negative 2 times this column, just minus that column. So we think so we can think negative 2 plus 1. So we keep the right 2 over 2 factored out. And we have negative 2 plus 1, which would just be negative 1. And then we have negative 2 plus negative 1, which would be negative 3. Okay, so it looks like we're heading to the point. So this will rotate to the point. You can multiply that in negative root 2 over 2, because I'm just multiplying it through to there and there, comma, and then we can say negative 3 root 2 over 2. Okay, so we can know exactly how things rotate here in this picture. Thanks for watching.